In this video, we will look at the low frequency responses of the DNA line filter and RxDNA with various series inductances that are present in the designs or in the facility. And a comparison will also be made to the old model, the existing model, and the model that is still available. This is the single final low frequency design. There have been several different configurations studied, and now we have closed in on a final design, and this is it. Let's look for a moment at the legend. There are 5 curves. We'll look at some of them in detail. The first one says RxDNA, and if you read across, it says 0.1 millihenries. But there is no series inductance in the RxDNA itself, so this 0.1 millihenry inductance is the inductance in the facility wiring. We'll look at that more closely in just a moment. The next curve is the M200, 0.25 millihenry. That's the orange curve. The yellow curve is an M30 or M100 with 0.5 millihenries. The fourth curve, the green curve, is an M20 design with 1 millihenry series inductance. And finally, the fifth curve, the maroon curve, is the existing M30, M20 with 1 millihenry. We'll scroll down here for a moment and look at the detailed data. You'll notice on the horizontal axis we have the log of frequency, and in the detailed data, the log of frequency is this column. The exact corresponding frequency in hertz is in this column. And these headings of these columns are exactly what we were just looking at in the legend. So they correspond one for one. As we look at the RxDNA case and the distributed facility inductance, here is some data. We'll scroll down on distributed inductance. The first column is wire gauge, then we have diameter in inches, diameter in millimeters, and then we have inductance per foot in microhenries, and you can see that they're all less than 1 microhenry. And the inductance per foot does not increase tremendously, little less than 2 to 1 as you go from quad-aught cable all the way up to gauge 18. For convenience, this inductance per foot at 50 feet, 100 feet, and 150 feet is given in a column. It's very important to understand this is just an idea to get us oriented towards what might be there in a facility. This inductance per foot is for a single conductor floating in space. In fact, in the facility, we have a hot lead and a neutral lead running together. And the magnetic field around the hot lead will be in an opposite direction from the magnetic field around the neutral lead, and they will tend to cancel each other so that the inductance per foot of a cable pair will be less than what you are looking at here. To give you an idea, gauge 8, roughly a 3 mm wire diameter. If we took two of those, one hot, one neutral, running parallel, and the center to center separation was 5 mm, this 0.314 microhenries per foot would be approximately 1/2 of that. So just so that you understand that this chart and the 100 microhenries, which is used in the graph that we're going to return to in a moment, is just an idea. The real test of what an RxDNA will do as a parallel element, as a shunt element in a facility, can only be known by plugging it in and testing it. So now we will continue on looking at some of the architectures of the distributed inductance. Here we will look at three ideas in terms of an effective series inductance for the RxDNA analysis. In this first diagram, we are talking about dirty electricity that is coming in from the street. It could be a neighbor who has solar, it could be industrial noise, it could be a utility company-based network-wide solar installation, which are becoming more prevalent. The transformer on the pole is the lowest impedance point, so it's being treated as the source here, the low impedance point, the signal generator, if you will, of the dirty electricity. The series inductance of the incoming line is the series inductance that can be used in the analysis of the effectiveness of an RxDNA in this sort of an application. Here, the RxDNA is being shown being mounted right at the circuit breaker box. We'll scroll down here to another possible. There are many, many possible architectures, as you know. Here again, we're talking about dirty electricity coming in from the street. So there is the lead length and the associated inductance coming from the transformer on the pole to the circuit breaker box, and then there is additional inductance in the facility wiring, and here the RxDNA is shown being mounted at a wall outlet. Scrolling down, another architecture is here the customer has their own solar installation, and incoming DC lead length is not of interest to us because the dirty electricity is being generated here in the solar inverter, and the lead length within the facility to the RxDNA is the presumed lead length inductance to be used in an analysis of the RxDNA. But there is more than that. The solar inverter has an output impedance, and that output impedance is part of the series impedance that the RxDNA is working with to attenuate the dirty electricity. The solar inverter designer designs the inverter to have a low output impedance at 60 hertz or 50 hertz, as the case may be. The solar inverter designer is not concerned with the output impedance at 16 kilohertz or 20 kilohertz or 25 kilohertz, but we are completely concerned with that. The solar inverter designer doesn't know what that impedance is and doesn't care. We don't know what the impedance is, the output impedance at 16 or 20 or 25 kilohertz, but we do care, and the only way we can assess it is literally to plug in an RxDNA and for the installing dealer, the biobiologist, to make measurements before and after. So whether the RxDNA is here at a wall outlet or the RxDNA is plugged in here right at the circuit breaker box, that test of before and after is the way to test the effectiveness of an RxDNA as the only element. Obviously, in this sort of an installation, a DNA line filter would be recommended, but it may be worth a try. And this is something an installing dealer could try before selling a product. So now we'll go back to the actual curves and look at that. Now we will look at some of the detailed responses of the curves. First, we'll look at the RxDNA. And this is the dark blue curve. So it is here, and it rolls off at a predictable slope. This is 10 kilohertz. And you can see that we're getting close to 20 dB attenuation at 10 kilohertz. Keep in mind that this is for a 100 microhenry presumed facility inductance. It might be 50 microhenries. It might be 10 microhenries. Again, we only know by testing it. But the point is here is that this roll-off point, if you come back here and see where this guy peaks a little bit, we're on the dark blue curve and looking where there's a little bit of a bump there. That's down fairly close to 1 kilohertz, which is a much lower frequency than the existing RxDNA. Now, let's jump to the last curve. This is the existing M30, M20, 1 millihenry series inductance, but not a low frequency model, not a low frequency model. So this existing product is shown here. And as with all of the DNA line filters, there was always a peak at around 1500 hertz, 1.58 kilohertz. And that's what you're seeing here. And then it rolls off. So you don't get any significant attenuation until fairly close to 10 kilohertz. This is the existing product. Now let's jump to the M20 product, 1 millihenry, because that is also 1 millihenry, and we can compare it to the one we just looked at, which is the green curve. And now you'll see that it peaks below 1 kilohertz, and in fact, at 1 kilohertz, an M20 low frequency model design has almost 10 dB of attenuation at 1 kilohertz. So let's keep moving down the green curve at 1.58 kilohertz. There is 17 dB, and at 2.5 kilohertz there is 22 dB. These numbers are very significant and very useful because there are neighborhoods, facilities, installations where there is energy, significant energy below 10 kilohertz in the 1 to 3 kilohertz or the 1 to 4 kilohertz range. So in the case of an M20, we would be providing some significant attenuation there in the low frequency model. Now let's go to the yellow curve. This is an M30 or an M100 with a 0.5 millihenry. And I know this is very crowded, but here at 1.58 kilohertz, we're looking at the yellow curve. We're seeing 10.3 dB of attenuation at just 1.5 kilohertz. And you can, of course, compare that to the existing product where at 1.58 kilohertz, we are actually amplifying the voltage, not the power, but the voltage of the dirty electricity signal. Then one more data point on the yellow curve, the M30 M100 curve at 2.5 kilohertz, we've got 16.4 dB of attenuation. And then you can look at the other models and look at the curves there. But this curve is probably about as busy as you dare get and still be able to get useful information out of it. Here is just a note in case it is of interest to you. The reason that the inductances go down as you go to higher and higher current is twofold. One reason is that the reactance, this is X sub L, the reactance of the inductor, X sub L equals 2 pi FL, is fixed for a given inductance. But that reactance in ohms at 60 cycles or 50 cycles drops voltage going to a load. And that drop is more significant as you go up in current. So by bringing the inductance value down, you minimize that. The other reason has been in the past, a secondary reason, is the availability of inductors in very high current capacity ranges. And if you found a 1 millihenry inductor that would handle 200 amps, it would be monstrously big and monstrously expensive. Now, because PAMA Engineering is now developing its own inductors, we will be able to offer higher inductances at high currents, but always we want to be aware of the voltage drop at 60 cycles. So there you have it. The new low frequency response curves for both the RxDNA and the DNA line filters. Thank you for listening. And one final note, there is, as always, an accompanying JPEG file with this video, and it is in fact the file from which this video was made, and you can download that and scroll through that and get any detailed data that you need or want.